What specific problem does your method aim to solve in the context of continual pre-training for MoE transformers, and why is this problem significant?
Our method aims to address the challenges associated with the continual pre-training of mixture of experts, MoE transformers, particularly the instabilities introduced by the routing algorithm and the need for balanced load across experts during distribution shifts. This problem is significant because, without effective load balancing, MoE transformers can overutilize certain experts, leading to poorer downstream performance and inefficient accelerator utilization. Additionally, existing load balancing algorithms were not designed for the non-IID data distributions encountered during continual pre-training, which can exacerbate forgetting and routing imbalances. By systematically studying and adapting routing algorithms like penalty-balanced and synchron-balanced routing, our work provides insights into maintaining performance and efficiency during continual updates, ultimately enabling MoE models to be updated on new data without the need for full retraining. This is crucial for leveraging the advantages of MoEs in real-world applications where models must adapt to evolving data landscapes.
How does the proposed method or algorithm work? Illustrate step-by-step the continual pre-training process for MoE models and the specific techniques utilized, including learning rate strategies and replay mechanisms.
The proposed method for continual pre-training of MoE models involves several key steps and techniques. First, the models are initially pre-trained on a large dataset, FineWeb, for 12 billion tokens, followed by continual pre-training on new datasets, Code and German Common Crawl, for 28 billion tokens. During this continual pre-training phase, two main strategies are employed: infinite learning rate (LR) schedules and replay mechanisms. The infinite LR schedule allows for a smooth transition in learning rates between continual learning phases, avoiding the pitfalls of fixed decay schedules that can lead to forgetting. Additionally, the replay mechanism involves reintroducing a percentage of previously seen data into the training batches, which helps mitigate catastrophic forgetting by reinforcing the model's memory of earlier distributions. The combination of these techniques enables MoE models to adapt to new data distributions while maintaining performance and minimizing routing imbalance across experts.
Can you provide a simple yet illustrative example of how the penalty-balanced TOP1 routing algorithm operates within your method? Walk through the main algorithm steps using a hypothetical token allocation scenario.
The penalty-balanced TOP1 PBT1 number 1 routing algorithm operates by dynamically selecting experts for token processing while ensuring a balanced load across them. For instance, consider a scenario where we have 3 experts, E1, E2, E3, and a batch of tokens that need to be routed. Initially, the router computes the logits for each expert based on the incoming tokens. The PBT1 number 1 algorithm then applies a softmax function to these logits to derive probabilities for each expert. Next, penalty terms are added to the overall loss function to encourage a balanced allocation of tokens among the experts. For example, if E1 receives 70% of the tokens while E2 and E3 only receive 15% each, the auxiliary loss will penalize this imbalance, prompting the router to adjust its routing decisions in subsequent iterations. The goal is to minimize the auxiliary loss, which promotes equal distribution of tokens, thereby preventing overutilization of any single expert and enhancing overall model performance. This mechanism is crucial for maintaining numerical stability and efficient parameter utilization in MoE transformers, as highlighted in the paper.
What are the theoretical and practical benefits of using the penalty-balanced and synchron-balanced routing strategies in your study? How do they compare to alternative approaches in terms of performance and resource utilization?
The theoretical benefits of using penalty-balanced TOP1, PBT1, and synchron-balanced TOP1, SBT1, routing strategies lie in their ability to maintain a balanced load across experts, which is crucial for optimizing performance and resource utilization in MoE transformers. Practically, our study demonstrates that both routing algorithms are robust to distribution shifts, as evidenced by their performance metrics, such as language modeling performance and maximum routing imbalance, MRI. Specifically, PBT1 MoEs consistently outperform SBT1 MoEs in terms of validation loss and overall performance, while both strategies effectively mitigate the negative impacts of distribution shifts. In contrast to alternative approaches, such as greedy routing, which can lead to overutilization of certain experts and poorer accelerator utilization, PBT1 and SBT1 routing ensure a more equitable distribution of computational resources, thereby enhancing throughput and reducing latency. Overall, our findings indicate that these routing strategies not only match the performance of full retraining baselines, but also improve sample efficiency, making them superior choices for continual pre-training of MoE models.
How was the effectiveness of your method validated? Describe the datasets used, the experimental setup, the performance metrics, and any benchmarks you compared against to demonstrate its efficacy.
The effectiveness of our method was validated through a systematic empirical study involving 4 different MoE architectures continually pre-trained on 28 billion tokens of code and German Common Crawl data, following an initial pre-training on 12 billion tokens of FineWeb. We employed a flop-matched dense baseline and a fully retrained penalty-balanced TOP1 routing, PBT1 granular MoE as benchmarks for comparison. Performance metrics included validation loss on both pre-training and continual pre-training datasets, as well as evaluation benchmarks for English, German, and code tasks, assessing accuracy across various tasks such as common sense reasoning and Python code generation. Our results indicated that all MoEs outperformed the flop-matched dense baseline during both pre-training and continual pre-training, with PBT1 MoEs consistently achieving superior performance compared to sync-Hern-balanced TOP1 routing SBT1 MoEs. This comprehensive evaluation demonstrated that our continual pre-training approach effectively maintains performance while mitigating forgetting, thus validating the efficacy of our method.
What specific results did you achieve with your proposed method? Highlight both quantitative and qualitative outcomes that reflect the model's performance compared to dense models and baseline approaches.
Our proposed method demonstrated that the penalty-balanced TOP1 routing PBT1 MoE model achieved performance on par with a fully retrained baseline while being significantly more cost-effective. Quantitatively, all MoEs outperformed the flop-matched dense baseline during both pre-training and continual pre-training (CPT), with PBT1 consistently yielding lower validation loss across datasets. In terms of qualitative outcomes, the PBT1 granular MoE exhibited robust performance on various evaluation benchmarks, including common sense reasoning and scientific question answering, indicating strong adaptation capabilities. Additionally, the continual pre-training with replay and infinite learning rate schedules resulted in lower maximum routing imbalance (MRI), suggesting improved efficiency and reduced latency compared to retraining approaches. Overall, our findings indicate that MoEs can maintain competitive performance and sample efficiency while effectively mitigating forgetting during continual learning.